So now we're going to be talking about the first derivative test, which is a concept in pre-calculus that is very important. So just a quick recap. What is a derivative? A derivative is basically it's basically the slope of a curve graph at a point. So what this means is, if I, for example, draw a graph right now. So this is the x-axis and the y-axis, and I have, say, this curve here, which is a quadratic function. And let me just try to make this look better. Okay. And then say I want to find the derivative of this point. So I want the derivative of this point on this graph. Then the derivative of this point on this graph would be the slope of this line. This red line that is tangent to this graph at this point. And we can find the derivative of any point on this graph if we know the equation of this graph. For example, if the equation of this graph is f of x equals x squared plus 5, then the derivative would be, using the power rule, we know that the derivative of x squared would be 2x and the derivative of 5 would be 0. So the derivative would be 2x. And depending on the point, depending on the point, we know the derivative. For example, if this point here had an x coordinate of 8, then we know that the derivative of f of 8 would be 2 times 8, which is 16. So the slope of this red line is actually 16. So that's a pretty steep red line there. So after a recap on what derivatives are, now let's move on to the first derivative test. So the first derivative test basically it involves a few concepts. Firstly, that the derivative or the infinite many derivatives of a graph, so like this entire graph right here, these derivatives, the slopes of each of these red lines, can be like graphed. So what I mean by this is, for example, so I'll draw the y-axis and I'll draw the x-axis. I know that when x is 8, which say x equals 8 is right here, the derivative of, no space. Let me just make this a little more vertically stretched out. So say x was 8. Then I know that the derivative of f of 8 would be 16. So we can graph the point here, or maybe more here. That's not that accurate, but whatever's. And then say we know that the derivative of f of 0 would be 2 times 0, which is 0. The derivative of, say, 4, the derivative of f of 4 would be 8. And the derivative of negative 4 would be negative 8, etc. So you realize that if you use a ruler to connect all of this together, which let's do that now, you'd get like in line. So I know this line doesn't exactly touch all the points, but that's because the points aren't that accurate after all. So we tried to make the points more accurate, then they should be like here and here. Like that. So essentially this is the graph of the derivative of f of x. So if, for example, if I wanted to find a derivative of this point, say the x coordinate was 2, then all I have to do is look at this graph and see, well, what is the y coordinate? What is the derivative of f of x as x is 2? Now we know by calculation, by this thing, that this y coordinate should be 4. So, or we can like look at the graph if we have an accurate grid or if this is on accurate grid paper, then we know that the derivative of f of 2 would be 4. So the first derivative test is based on the idea that you can actually graph out all the derivatives in a graph f of x, and that you can essentially link all of these infinite number of derivatives together. Now notice that this is a quadratic function. Well, I mean, that's pretty obvious, but like, yeah. So this means that if I draw the other side of the x-axis, the negative half, that the graph would look something. The graph would look something like this. Right? So what if I wanted to find a derivative of a point on on the negative half of the x-axis? Then this means that I need the slope of this other red line right here, which the slope is obviously negative. So the derivative is negative. And notice that if I like graph out as much points as possible on the negative half of the x-axis, notice that all these slopes are going to be negative, while all the slopes on this side of the graph are going to be positive. So this actually reflects on the derivative on this graph of the derivatives, right? Because when x equals 0, which is this point right here, when x equals 0, we can draw a tangent line, and you can clearly see that since that the derivative here is 0. And to the left side, on the negative half of the x-axis, the derivative is negative. On the positive, the derivatives aren't all negative. And to the right half, the positive x-axis, the derivatives are all positive. So the first derivative test is based on this, and the formal definition is basically if we're given a continuous and differentiable function f, so that basically means continuous. So continuous basically means that there's no gaps or holes in the function. So for example, a quadratic function is continuous, but a piecewise function might not be. So an example of a function that's not continuous would be, so that's x, that's y, and it would be like here. So that could be an example. And here the function is discontinuous at several points. At this point, and probably at some other points. So as you can see, being discontinuous basically means you can't draw this function without lifting your pen. So you have to do this, and then you have to lift your pen up, and then you have to do that. Lift your pen up, and etc. So being continuous is the opposite. It means there's no gaps or holes. So the function wouldn't be like that, so there wouldn't be a sudden hole in the middle. So there's no gaps or holes in the function. And it's differentiable. What this means is that all of these points on the graph, you can take the derivative. So it basically means if I graph out the derivative of f of x for my function, there would be no gaps, or there would be no holes in this function. So this function here would be continuous for f of x to be differentiable. So now if the function f is both continuous and differentiable, and c is a critical point or critical number, or its turning point or saddle point, whatever you call it, then f of c, then we can look at f of c in two ways: local, or not local, relative minimum or relative maximum. So basically, essentially what this means is, so firstly, what's a critical point? So a critical point is basically like a point in the graph of, so a point x equals c, where the sign of the derivative of f of c changes. So like where the sign of the derivative of f of x changes when x is less than c and x is larger than c. So what this means is, for example, so the sign means the positivity or negativity. For example, x equals 0 would be a critical point in this quadratic function, because when the derivative of f of x is, so the derivative of f of x is less than 0 when x is less than 0. And the derivative of f of x is larger than 0, so it's positive here, as you can see, when x is larger than 0. So this means that x equals 0 is a critical point. So essentially what this says is, and we can classify x equals c, this critical point, into two types. Type number 1 is the relative minimum. It's basically when this happens. So the relative minimum is basically when the derivative of f of x is less than 0, when x is less than c, and the derivative of f of x is larger than 0 when x is larger than c. The second type is relative maximum. So this is when the derivative of f of x is larger than 0 when x is less than c, and the derivative of f of x is less than 0 when x is larger than c. So relative minimum is basically when, so if we graph this, it's basically, say this is the critical point. Before the critical point, the graph has a negative slope, like that, and then after the critical point, the graph has a positive slope. kind of like, you can imagine the quadratic graph facing upwards. And this would be the relative minimum here, right? And the relative maximum is the exact opposite. As you can see from the word maximum, this is the highest point in this area of the graph. So say this is the critical point. You can imagine a quadratic facing downwards.